Hello, my name is Nicholas Bergeron, and today I'm going to be going over Lab 5, our final lab for Physics 2212. So, in this lab, we are testing the magnetic field of a piece of aluminum foil by dropping a magnet through it. And in this, we are going to use several laws, which are not limited to, but including Faraday's law, the Biot-Savart law, and Newton's second and third laws. And all four of these laws are going to play a crucial part in our later calculations of the various forces at play here. So, first, here's the video of me dropping, it's slow motion, but here's a video of me dropping the magnet through. There you can see, play it again. I did this 5 times. I only showed you guys once because I don't want to have 5 videos on the slide, of course. And the average fall time was 0.512 seconds. And my MU from lab 3, I believe, is 0.2937 A times M2. And then the tube length is 0.15 meters, and the diameter is 0.019 meters. So, as we can see from the GlowScript code, here's a screenshot of the direction of the current. The red represents counterclockwise when we are facing down on it, and by Faraday's law, if the magnet is dropped in a reverse orientation, the current would have been counterclockwise. So the differences in calculation here is that the time that I found the average from was 0.512 seconds, and the calculated time from my GlowScript code is 0.649 seconds, which is an error of 26.8%, which might seem pretty substantial, but there are several different ways that error can happen. The EMF field in the room can be different. I did in a room that has a stereo. We have a TV in there just because there's really no other place for us to do it where we have no electronic appliances. Also, I believe that the magnet made contact with the side of the tube a bit, which could slow it down, cause some friction. So those are just 2 examples of some error that could cause that difference. And here is the velocity time graph that I was given after using the GlowScript code. As you can see, once we go past, we have a mostly constant velocity right here with a slope of 0, since this is a velocity time graph. So with a flat line, we're going to have a constant velocity, no acceleration. So F net is equal to 0. And both the beginning and the end have decrease in velocity, and this is because the magnet is so far outside the realm of influence. Well, for the first time right here, it's because the magnet is within the realm of the sphere of influence of the magnetic field of the tube, and it is counteracting the downward motion of the magnet, and it's pushing back up. But then down here, it is decreasing velocity because it has left that sphere of influence, and gravity is just more powerful than the EMF of the tube is. So F net is no longer equal to 0 just because gravity is stronger in the latter part of this graph. Now, some what ifs. If the resistivity of the conductor was reduced to almost 0, there would be a much slower fall and a longer time, just because there would be a lot higher there would be more charge going through the tube, and also since the EMF remains constant, R is going to be much smaller than I. So as I increases, FB increases, so FB is going to be much greater than FG. So like I said, a slower fall and a longer time that it is in the tube. Now let's say some holes or slots were cut in the tube, the current would be disrupted and the EMF would decrease. So therefore, faster fall, shorter time. And that's all for Lab 5. I'll drop my GlowScript code in the video description below. Thanks for watching.